Hello students, this is Dr. Munir Omar with CS 371 Data Communication and Networks. Today in lecture number 32, we will be studying about the error detection. We have already studied about the impairments, in which we studied that the transmitted data may get corrupted during the transmission, and it is possible that the received data would not be similar to the transmitted. So the corrupted data is caused by the corrupted bits, and we refer such scenario as error in the received bits. So in today's lecture, we will study about the detection of such corrupted or changed bits. By the end of this lecture, you would be able to understand the basic concept of an error in computer networks and its types. By computer networks, I mean the data communication or the transmission of data from one host to another. In this lecture, I will explain different type of error detection codes and how does error detection take place in data communication. I will also discuss few well-known error detection techniques in details. These are the contents for our today's lecture. First, we will define the error and its types. In this lecture, we will define the two types of errors. Then we will discuss the process of error detection. We use redundant bits for the detection of errors. Then we have some methods for detecting errors. These are vertical redundancy check, then longitudinal redundancy check. These two use parity bit mechanism. So we will also study about the parity bit. Then we have cyclical redundancy check. We can also call it cyclic redundancy check, CRC. And at the end, we will have the checksum. We will look into all these detection mechanisms, and we will have some examples for these. Okay, let's start with error. Whenever a message is transmitted, it may get scrambled by noise or data may get corrupted. If the transmitted bits are changed or lost, then we can say that that transmitted data got corrupted. Data can be corrupted during transmission. This is obvious because the transmission medium is not perfect. So any type of data can be corrupted. For reliable communication, errors must be detected and corrected. This is the need of data communication, that the errors must be detected and corrected. Error detection and correction can be implemented at Datalink Layer and Transport Layer. Data can be corrupted during transmission. Most of the applications require that errors be detected and corrected. There are two types of errors: single bit error and burst error. Single bit error. In a data frame, there is only one bit which is corrupted. This one bit can be anywhere in the data. So here we have 8 bits transmitted, and this 0 got changed, and the received 8 bits are different. Here we have 1 instead of 0. So this 1 bit is changed, and this error is 1 bit error. In a single bit error, only 1 bit in the data unit has changed. Then we have burst error. Data frame is received with more than 1 bits in the corrupted state. Errors do not occur in consecutive bits. The length of the burst measured from the first corrupted bit to the last corrupted bit. So first thing, there might be more than one bits here. If we look into these bits are sent and these are received. So some of the received bits are different from the sent bits. These are actually corrupted bits. So these are more than one. Second thing is that there isn't any condition of consecutive bits. Now if we look into these two bits, these are consecutive, but the burst is known for non-consecutive multiple bits. Third thing is the length. The length is measured from the start till the end, from the first corrupted bit till the last corrupted bit. So this is the length, and this length is equal to 8 bits. A burst error means that two or more bits in the data unit have changed. Then we have error detection. We use error detecting codes, which are additional data added to a given digital message. If we are sending data, then for error detection, we also add some additional data, and that is also transmitted with the original data. The additional data helps us detect if an error occurred during transmission of the message. To detect or correct errors, we need to send extra bits with data. These extra bits are also called redundant bits. Error detection with redundancy. The simplest way is to have two copies of data unit. For sending, we have two copies and we send both the copies. At receiving side, these both copies are compared. If both are equal, means that there is no error. This is the simplest way. But if we apply this thing or implement this thing, what will happen? It will double the transmission time, and also the computational time will be slower. So for redundancy, only extra information is added, and this information is less than the actual data. Shorter group of bits may be added to each packet, and these additional bits are received by the receiving device, and if the receiving device detects an error, then it discards the received packet, and if it detects that there is no error, then the data is accepted and the additional bits, the redundant bits, are discarded. So this diagram shows the process of adding redundant bits and then redundancy check on the receiving side. First, data is taken, then a function is applied on the data, and some redundant bits are appended with the data. So the sender was supposed to send this data, but it sends this entire block, which is composed of actual data and the redundant data, which is generated by a function. At receiving side, the receiver apply the similar function, and if there is no error in the data as per the process, then accept the data, and if there is an error, then that data is rejected by the receiver. There are four types of redundancy checks. The first one is vertical redundancy check, VRC. The second one is LRC, longitudinal redundancy check. Then we have CRC, cyclical redundancy check, and the last one is checksum. So we will study all these in the coming slides. Parity bit. One additional bit is added with the actual data to make the number of ones even or odd. So we will have even parity or odd parity. The additional bit would be called as parity bit. So for redundancy check, we use parity bit. The parity bit can be set to 0 and 1 depending on the type of parity required. Let's say for this example, we need even parity. So here we have 1, 2, 3, 4, 5. 5 ones. So we must make these ones as even. So here we should provide 1 as an additional bit. Now here we would have even number of ones for even parity, and if we need odd parity, in that case we must provide 0 here, so that the number of ones in this entire block data plus parity bit must be odd. The first redundancy check in our list is VRC. VRC uses the parity bit. It is the most common and least expensive mechanism for error detection. As we know, in parity bit, a redundant bit called parity bit is appended to every data unit so that the number of ones in the data unit becomes even or odd. So, for adjusting the even and odd number of ones, we set the value of parity bit to 0 or 1, as we did here by providing 0 or 1 to make the number of ones even or odd. Now here we have data, and this 1 bit is appended with this data to make the number of ones as even, because we need even parity and the function is used even parity generator. So here this additional one is VRC, and this block is data. This entire block data plus parity bit is transmitted to the receiver, and at the receiving end the receiver counts the number of ones, and if these are even, then the data is accepted, otherwise the data is rejected. So this VRC can detect only 1 bit error. The VRC is designed to detect all single bit errors. However, it can detect 1 bit error, 3 bit error, 5 bit error, or we can say that odd number of bits that are changed can be detected by VRC. It cannot detect errors where the total number of bits changed is even. Then we have longitudinal redundancy check LRC. Parity check bits are calculated for each row, which is equivalent to simple parity check bit. This is actually two-dimensional parity redundancy check, and in this check we take multiple bytes and calculate their parities under those bytes. Parity check bits are also calculated for all columns. Then both are sent along with the data. At the receiving end, these are compared with the parity bits calculated on the received data, and the result is concluded. This one is also known as two-dimensional parity redundancy check. So here let me show you this example. So here, if you look into this data is supposed to be sent by the sender. So there are 4 bytes. So what happens for each column in these 4 bytes, or we can say for each bit in these bytes, we calculate a parity. So for first bit in each byte, we are calculating one parity. Here we need even parity, so this one is actually odd, the number of ones is odd, so we must add 1 here. Here again, this one is odd, so make it even. This one is already even, so no need to provide 1, so we are giving 0. Similarly, ones and zeros are given to all the columns. So this data plus the calculated parity bits are sent, and at the receiving side the same process is adopted and checked whether there is any error or corruption in these received bits. Here we have another example. We have 4 bytes. These 4 bytes are taken, and for each column in these 4 bytes we calculate a parity bit, and we make even or odd parity. So here we have odd number of ones, sorry, even number of ones. So 0 is given, here only 1 is present, so odd number of ones, 1 is given to make it even. Similarly, zeros and ones are given, so this one is actually the LRC, and this LRC is appended with this actual data and it is transmitted. So the original data plus LRC is transmitted, and at the receiving end the receiving device calculates the even or odd numbers according to these blocks and these parity bits and conclude a result. Then we have cyclic redundancy check, CRC. CRC is performed at Datalink Layer. It is based on binary division. What we do, we take the data, append some zeros with it, and then apply a division having a divisor. So the appended bits, let's say we have n bits, so the divisor should be n plus 1 of length, and after that when we divide this whole thing on the divisor we will get a remainder that would be called as CRC. The data plus CRC is sent, and at the receiving end again the same divisor, this one divisor is used for dividing this data plus CRC and check the remainder. If remainder is 0, then accept it, otherwise there would be some sort of corruption in the data or CRC. Here we have an example. We have data, this one has to be sent, so what we do, we are appending 3 zeros with it, and the length of divisor is 1 greater than these 3 appended bits, so it should be 4 bits. And if we divide this data on this divisor we will get 001 as a remainder. As we know that during the division we use the XOR operation, so if we have 1 1, then it should be 0 for 0 0, it should be 0 for 0 1, or 1 0 it should be 1, so for 1 1 it should be 0, for 0 0 it should be 0, and for 1 0 or 0 1 it should be 1 here. So we are using XOR operation here, and at the end we get the remainder. So what happens, this remainder is appended with this data. A CRC checker functions exactly like the generator. At receiving side, CRC is used, and at the sending side, the CRC generator is used. Both work in the same way. Data plus CRC is divided by the predefined divisor at the receiving end. So if the remainder is all zeros, then it is accepted. Otherwise, the data is discarded because that data would have some sort of error. Here we have an example. Data to be sent. This one is the data. So it is here. We appended 40. This is actually 4 bits. So we appended 4 bits with this data. So the divisor must be greater than 4. It must be 5. So this one is the divisor. Now if we perform this division, we will get this value as a remainder. So this one is actually our CRC. At receiving end, we will get the data plus the remainder or CRC. So both are divided by the same divisor, this one, and at the end we will get zeros if there is no corruption in these bits. Otherwise we will get some value here rather than 0, and in that case the received packet would be dropped, or the received data would be considered as corrupted. CRC polynomial, CRC generator, the divisor, is also represented as an algebraic polynomial. It can be used to prove the concept mathematically. So here we can use such type of polynomial notations to represent the CRC generator or the divisor. Here, let's say we have a polynomial, this one. So this one is x power 0, x power 1, x power 2, x power 3 is skipped here, x power 4 is skipped here, then x power 5 and x power 6 is skipped. So for the present values, we are giving 1. So here we have 1s. For x power 3, there should be 0. For x power 4, there should be 0. And similarly, for x power 6, there should be 0. So this one is our divisor, and this divisor is represented by this polynomial. All burst errors of a length equal to the degree of polynomial are detected. These are some standard polynomials. For CRC 12, we have this divisor. For 16, for CRC ITU, and for CRC 32, we have this polynomial. We have one another example. Here we have the original message which has to be transmitted. Then we have a polynomial x power 3 plus 1. So it is actually x power 3 plus x power 2 plus x power 1 plus x power 0. So if we convert this into the bits, it should be 1, then 1 for x power 0, and these two zeros are for x power 2 and x power 1. So this is our 4-bit CRC generator. Since we have a 4-bit CRC generator, this is given, so we must append 3 bits, 3 zeros with the original data. Now we are using this divisor and data plus 3 zeros, and here we are having XOR operations. During the division at the end we will get a remainder. This one is the remainder. Since we appended 3 bits here, so we will also take the 3 bits from the remainder, the LSB bits, and append those 3 bits with the original data, so we will get this block of bits. Now this block is transmitted. At receiving end, same divisor which was applied here is used, and the data received is used here. Now if we process this division, we will get zeros here because we have same data at both ends, so there is no corruption of any sort of corruption of bits, so definitely there would be 0 in the remainder. Let's say we have 0 here. This one is, let's say, corrupted or changed during the transmission. The actual value is 1, and here we have 0. So what will happen here? This would be 0, and at the end in the remainder we will have 1, which is representing that the data has been changed. Another example for CRC, here we have the data, and this one is the divisor. Now if we look into the divisor, it has 6 bits, so we must append 5 bits or 5 zeros with this data and do divide this entire block on this divisor. So after the division we will get a remainder, and then we must append this remainder with this data. So here if we look into the number of bits or the number of zeros appended is 5 and the remainder is 4, so here we must append 5 bits with the data, and the remainder here is actually 4 bits, so here we must also supply one additional bit. This entire block is now ready, and this one will be transmitted. At receiving end, same divisor will be applied on the received data, having the actual data plus the calculated remainder or the calculated CRC. So after having the division, we will get remainder as equal to 0 because all the bits are not changed. So in case if any of these bits is changed, then this remainder would not be 0. Checksum is used to check the corruption in data. This is used for checking errors if occurred in the received data. The sender calculates a short value known as checksum and sends it with the data. On the other side, the receiver also calculates the checksum. The receiver takes the sum of the received data with received checksum, and if the receiver at the end gets ones for the entire result, then there would be no error, else there would be some sort of error in the data, and we will say that the received data is corrupted. Imagine we have a UDP segment or a TCP packet. The first thing that we do is to divide and slice up it up to 16-bit pieces. So here, let's say we have 48 bits, so we must divide it into 3 parts, each having 16 bits. Now these are 48 bits, 16 plus 16 plus 16, and the sender needs to send this data. So what will happen? The sender will add these three blocks of 16-bit each by using binary addition, and below the sender will get 16-bit of data for this binary addition. After that, the the calculated bits are considered, and one's complement for the calculated sum is calculated. One's complement for these bits is calculated. So this calculated one's complement is actually our checksum. We need to basically send our data. So this is the foremost thing for us, which we divided into blocks of 16 bits. And with this data, we also have a checksum which we calculated by taking the sum of these the blocks of 16 bits each, and then took the one's complement of the summation. The main thing to understand is the receiver will get the data as well as the checksum. So here we have three blocks, 48 bits, and the receiver will get these 48 bits plus 16 bits checksum. So the receiver will get 64 bits. These three blocks of data plus this checksum will be received by the receiver. The receiver will simply add all the above four blocks. All these blocks will be added. Data as well as checksum are added together. So if we add all these, we will get these 16 bits. All the fields will be ones. In case if there is no corruption in the bits, then the receiver will get all the 16 bits as ones. And if there is even a single zero in these 16 bits, then it would be assumed that there is an error induced during the data transmission. Let's consider a proper example for UDP checksum calculation. We are going to send this data which is testing. So we have 1, 2, 3, 4, 5, 6, 7. 7 characters. One character needs 8 bits. So as earlier we saw that for checksum we need these blocks of 16 bits. So what will we do? We will add 8 zeros with this data to make a complete block of 16 bits. So we will have block 1, then block 2, block 3, and this one would be block 4. Adding this block of 0 or adding these 8 bits is known as padding. UDP checksum calculation includes 3 sections. This one, the pseudo header, then UDP header, and data. The pseudo header is the part of the header of the IP packet in which the user datagram is to be encapsulated with some fields filled with zeros. If the checksum does not include a pseudo header, a user datagram may arrive safe and sound. But if the IP header is corrupted, if we get some corruption in these addresses, let's say, it may be delivered to wrong host. The protocol field is added to ensure that the data packet belongs to UDP and not to TCP. So for this IP address, we need 4 bytes, means 2 blocks of 16 bits. So we are taking these two octets, 153.18, 16 bits, and 8 bits and 8 bits, then 8.105. Here we have 16 bits. Then for destination address, we have 16 plus 16 bits. Then we have the protocol and length. So for here we have 16 plus 16. Also we padded some zeros. After that, port numbers, the port number of source as well as destination process. Then the length of UDP header, then the length in UDP header. After that, checksum, this one, and then we have the data. So if we calculate the binary sum of all these blocks of 16 bit each, we will get this sum. And if we take 1's complement of this sum, we will get this checksum. So at sending side, all these bits are sent along with this checksum, and on receiving side, all these bits and this checksum are added using binary sum. And if on the receiving side ones are computed, then we will say that there is no corruption in the data. Otherwise, the data would be corrupted. We have an example for calculating the checksum. So here we have the header and we have some values in this header. So here, if you look into this header, we have 32 words, 32-bit words. Like here we have 32 bits, then 32 bits, 32, 32, 32. In the previous example, but we did this. In fact, for checksum, we need 16 bits. So we are going to take 16 bits from here, 4, 5, and 0, convert it into hexadecimal, then 28, convert it into hexadecimal, then here 16 bits, 1. This one is converted. Similarly, all these values are converted. The IP addresses are also splitted into two parts. 1012 is taken, then 14.5 is taken. So then sum is calculated of all these hex, and 1's complement is taken of this sum. So this one is the checksum for our header. It is just like transport layer, but that time we converted the fields into binary bits. There were blocks of 16 bits.